In this video, we're going to be considering the piecewise-defined function where one of the pieces is a line, 5 minus x, and one of the pieces is a square root function, the square root of x plus 1, so it's going to be a shift of the typical fundamental function that's the square root of x. And the split here in the domain is going to be x less than 3 for the line and x greater than 3 for the square root function. So first we're going to just warm up by evaluating here. So f of 0, for 0 we're looking at the input value x equals 0. Well, that would fall in the interval x less than 3, so we're talking about the top piece here because 0 is less than 3. So we can evaluate this function then, this piecewise defined function, by evaluating it in the correct piece. So we'd do 5 minus 0 and our output value is 5. Moving to the next one, our input value is 3. So when we look at 3, we realize 3 is not less than 3, and 3 is not greater than 3 either. Since neither one of those inequalities allows for equality, we don't have a place to stick the input value of 3. And so we should say here, neither piece. And so this we would then consider undefined. That 3 is not in the domain. So finally, looking at 7, 7 is greater than 3, so that falls in the x greater than 3 domain restriction. So this will be our bottom piece. And so when we plug it into the bottom piece, we've got the square root of 7 plus 1, so that would be the square root of 8. Now, 8 is not a perfect square, but it does have a factor that is a perfect square. And so we can figure out a little bit how to clean this up by factoring this 8 as 4 times 2. Now, 4 is a perfect square, so we can pull it out of the square root by taking its square root. So the square root of 4 is 2, and then we're left with the square root of 2. So that is how you handle the simplification of that radical there. All right, so we've done some evaluation. So the next step is going to be graphing this function. So my suggestion for always on graphing these piecewise defined functions is to graph each individual piece and then look at the domain restriction before putting it together. So let's take a look at the line 5 minus x. So the line 5 minus x, we're talking y is equal to 5 minus x. It would have the y-intercept of 5. See, perhaps you're thinking about this as y equals negative x plus 5 if you were looking at it as like the y equals mx plus b form, the slope-intercept form. So our y-intercept up here is 5, and it has a slope of negative 1. And so that would be going down 1 to the right 1, or we could think down 5 to the right 5, and so its x-intercept over here is actually 5 also. And we can connect and draw our line. So that's over the entire domain of that line, and we'll do the restriction here in just a moment. But let's first get into the second piece. This second piece is the square root function. Now, the square root function is really kind of the top half of a sideways opening parabola, but we've got to shift it over because of the plus 1, we've got to shift it in the x direction left 1 because of the plus 1. And so this is really the parabola looking like this, the half of the opening parabola. So that's the square root function that's shifted. Okay, now this anchor point here for that square root function is going to be at the negative 1 because we had to shift it to the left 1. Okay, so that would be our two individual functions over the entire domain for those functions, but we want to restrict the domain. And that restriction of the domain is going to happen at 3. And so here we would have a point that would be open because we don't have the or equals to case, and that's going to be there at the 3, and we're going to be only taking values that are to the left of 3, so that would be this part right here. Okay, now moving to 3 here for the square root function, it'll be somewhere over here Again, it's open because its x is greater than 3, and we would be taking to the right because of the greater than part. Open because of the not equal, and to the right because of the greater than. So now we really want to know where that switch is happening. As we know it's happening at x is equal to 3, so we could go ahead and mark that as an important value for the x's, but we really need to know what important value corresponds to it for the y's. And so let's just calculate that here. Y would be equal to 5 minus 3 if we're talking about what's happening exactly at 3 there. 5 minus 3 is 2. So we know that this important y value is 2 for the line. Now when we're looking at the square root function, I forgot to write it over here, y equals the square root of x plus 1. And when we're trying to evaluate to figure out what our important y value is, it would be y is equal to the square root of 3 plus 1. Well, that'd be the square root of 4, which is 2. So notice that's actually the same important y value that we had come up with before. All right, so now let's take a look at how we can put this together. As we are putting our graph together, we want to make sure all of our important x's and y's are labeled. And perhaps we don't want to label anything except for those important ones. And so 3 is really our primary important place. That's where the switchover is happening. And for both, when x is equal to 3, y was equal to 2. And so we're going to see that that's an important place for both. Now this y equals 5 is probably a good one to go ahead and draw in also because of our line that needs to be going here. Let's see. We have the 3, 2 point, and it goes through the y-intercept that we had. Okay? So that would be the part that was coming from our line, and now the part that's coming from our square root function is now starting at that same hole that is 3, 2, but this time, we've got the kind of arched square root function taking off there. And so that would be our complete graph of the piecewise-defined function. So let's copy this graph here. So we'll copy it, and we'll paste it over here. Get it in here. Get it situated. All right. And we want to look at the discontinuities. And so as we're taking a look at this function, kind of maybe from the left to the right so we don't miss anything, the only thing that's happening that's kind of strange is at that switch in the domain at 3. And so that does happen to be a discontinuity. The pieces do end up coming together, but that 3 value for the input wasn't allowed. And so it is a discontinuity because it has a missing point there. And so we have this discontinuity as x is equal to 3. So we want to look at what type of discontinuity it is in any one-sided continuity. So to look at the type, the first thing we always rule out is it an infinite discontinuity? And since I have no vertical asymptote there at all, neither one-sided limit is going off to plus or minus infinity, it is not an infinite limit. So now that we've ruled that out, we've got two options. Is it a jump discontinuity or is it removable? And so the way we decide which of those two options it is we know that it's a jump if the two one-sided limits do not come together, and it is removable if the two one-sided limits do come together. And so here we do see that the one-sided limits do come together, and so we will say that this is a removable discontinuity. Basically, it looks like I just took that single point and I removed it. I plucked it out. Otherwise, if it were included, if it was a solid dot there instead of an open dot, it would be continuous. So removable discontinuity, in some sense, is a pretty minor discontinuity. And we got that from the left being equal to the right after we ruled out that it was not an infinite discontinuity. Okay, so we know the type of discontinuity and we want to assess any one-sided continuity. And to figure out one-sided continuity, we look for the solid dot. And at 3, there is no solid dot. We found out when we were trying to evaluate that f of 3 was undefined. And so this is neither right nor left continuous. All right, so neither right nor left continuous, and that's really because f of 3 is undefined. Or you could think about this as no solid dot. Okay, that's really our reasoning there. Okay. And so now we have looked at a different sort of piecewise defined function. We've done some evaluation of various input values for the piecewise defined function. We've graphed it by looking at the individual pieces in their entireties, and then only restricted it to the part that we cared about to be able to piece them together for our entire function. Once we have the graph, we can answer these calculus type questions of discontinuities and types and one-sided continuities and so forth by looking at the graph and making those observations.